We have an interesting mix of talks. You have to switch context a lot. First speaker is Yang Liu, and he changed his title. So.
I saw what everyone else was talking about, and I decided to talk about something which seemed to fit a little more in terms of what everyone else was doing. So I'm going to talk about a problem that I worked a lot on during my PhD and that I'm very excited about. I'm going to talk about graph algorithms, convex optimization, and the maximum flow problem. To start, I should probably define the maximum flow problem. In this problem, we have in the simplest form of this problem, we have a directed graph G with vertex set V, edge set E, and just to set up some notation, we'll say that there's M edges and vertices, and two special vertices S and T, which we call the source and the sink. In this problem, our goal is to design a fast algorithm that will find the maximum number of edge disjoint paths in this graph between S and T. So in this example, the maximum flow value is 3 because there's exactly 3 edge disjoint paths between S and T that we can find, and we can't find any more no matter what we do. This version of the problem already captures some other combinatorial graph algorithm problems, such as the bipartite matching problem. In this problem, we have a bipartite graph with edges between the left and the right, and our goal is to find the maximum number of edges in this graph that don't share any vertices. So here, the maximum bipartite matching happens to contain 4 edges, which is the maximum number possible. As I describe slightly more general versions of the maximum flow problem, I'm going to add some more applications to this slide. In the slightly more general version of the maximum flow problem, which I'll call the capacitated max flow problem, we still have a graph G with M edges and vertices, but now every edge has an additional integer associated to it, which I'm going to call its capacity. And we'll let U denote the maximum capacity. Now, so now in this problem, our goal is to find the maximum flow between S and T in this graph that satisfies the capacity constraints. Put in the context of the first slide, we now want to find a set of paths such that for every edge, the maximum number of times that any path. UE now upper bounds the maximum number of times that edge E can be contained in any of the paths in our set of paths. Because this problem has a lot of different applications, it's been widely studied since its introduction in graph algorithms. And some of the algorithms that have been proposed for each of the settings are, for bipartite matching, you can get an algorithm running in time M times square root n, where remember M is the number of edges and n is the number of vertices. You can get a similar bound for the general max flow problem on a graph with no capacities of M root m or M n to the 2/3. And finally, in a seminal result of Goldberg-Rao, they show that you can match this runtime for the case without capacities, even if you have capacities up to logarithmic factors. These results, I'll call them all combinatorial algorithms for maximum flow, because they all have a very combinatorial nature in the following way. They take the following very natural approach to finding a max flow in the graph, where I find a path between S and T, or maybe a lot of paths all at once. I'll add all the paths to my set, and then I'll update the graph, and I'll repeat this some number of times until I can show that my algorithm has converged. This is called the augmenting paths algorithm for the maximum flow problem at a very high level. More recent advances in this maximum flow problem don't take as much of a combinatorial view. And to get into that, I'm going to introduce what I'm going to call linear algebraic formulation of the problem that is completely equivalent. Now we once again have the same graph where every edge still has a capacity on it. But now instead of thinking of the flow as a union of paths, we're going to think of it as just an assignment of a vector f to the edges of the graph, where fe is the amount of flow we're going to put on the edge e. So for example, this is what I'm going to call a flow. This flow needs to satisfy 2 properties to be compatible with the path-based definition. The first is that the amount of flow on edge E needs to be at least 0, and at most the capacity UE. Also, if we add an edge between T back to S, and the amount we put on the edge equals the amount of incoming flow to T, then every vertex also satisfies that the total net flow is zero, that the total incoming flow equals the total outgoing flow, including at S and T. In this formulation, the max flow problem asks to choose a real vector f on each of the edges that satisfy these two constraints, and to maximize the value of this edge from T to S that we've added. And you can check that this is completely equivalent to the path-based formulation. In particular, and I guess it might be interesting to note that I have no like integrality assumptions on f. You can just assume it's all real numbers, and the problem is still completely equivalent. In this way, we can write the problem again in a linear programming formulation. We want to find a flow vector f that satisfies the capacity constraints, that it's with at least zero and at most UE on every edge, and that it satisfies a linear equality constraints on every vertex. So here B is called the edge vertex incidence matrix, and you can just think of it as the matrix that captures the fact that at every vertex, the incoming and outgoing flows match. In other words, the total sum is zero.
Sorry, when you said it's equivalent, you mean if you run the real version of the program in an integer setting, the answer will be integral?
That is correct. That is correct. Okay, now we want to minimize negative of the amount of flow on the new edge that we've added. The reason I wrote it this way is because now it's easy to study more general versions. In the minimum cost flow problem, the objective no longer is to minimize the negative of the flow on the new edge, but we just want to minimize some linear function of the flow. So C is just another input vector, and this is what we want to minimize. This is called a minimum cost flow problem. So I guess written in this way, it's even more clear that maximum flow is exactly linear programming specialized to a graph. And just to generalize one more time, we can replace these linear cost functions on the edges with convex cost functions. Cost here is just an arbitrary convex function on the edge E, and FE once again is the amount of flow. Once we've generalized the problem to this extent, well, we can start capturing many problems beyond bipartite matching. Once we've added capacities and costs to our problem formulation, we start capturing many other things. For example, what I called it is minimum cost flow. But you can also start to find shortest paths in graphs between pairs of vertices, even if the graph has negative edge lengths, and also captures this matrix scaling problem with the convex cost formulation and a variety of others. What I'm going to hopefully tell you a little bit about is some work I did in my PhD with several co-authors, where we showed that all these problems that I've talked about so far can be solved in almost linear time, n to the 1 plus little o of 1. So recall that m was the number of edges in the graph, so that's the input size. So what this means is that the runtime to find a solution to any of these problems is m to the 1 plus epsilon, basically. Hopefully in the rest of the talk, I'll be able to tell you a little bit about how this works, but obviously I can't get too much into detail.
One question.
Yes.
Say to high accuracy, since you were bounding everything in term of m,
Yeah.
like you were bounding the maximum capacity in term of m, can you actually drop the high accuracy part? Because I mean, the answer is really, I mean, if everything is integer in the very beginning.
Good, yeah. So the question was, can you drop the high accuracy? And the answer is for max flow and minimum cost flow, you can show that the optimal solution is indeed integer, so you can drop it. But for these convex problems, it might not have an integer solution, so in that case, it's better to just say high accuracy.
But what does the high accuracy mean?
In general, when in algorithm you say high accuracy, it means if you want accuracy delta, then the runtime depends logarithmically on delta. So in terms of previous work, I won't spend too long here, but there's a couple of different phases. In the first is once again combinatorial algorithms, where the algorithms were based on finding paths between S and T in some phases. And these got to runtime about m root m. The way you can think of this is that the algorithm has about root m phases, and each phase takes linear time, basically one scan through the graph, and then you find the flow. In the next phase, there were a lot of algorithms based on continuous optimization methods. These kind of directly treat the Maxwell problem as its linear programming formulation and apply linear programming techniques, obviously with a lot of additional tricks to get improved runtimes. As a baseline, these algorithms also have a similar type of behavior. They have root m iterations, where each iteration does a scan through the graph costing m time. So m to the 1.5 is the baseline, and there are various additional techniques needed to improve on that. And you can by a little bit. What I'm going to tell you a little bit about now is the almost linear time algorithm, where it looks slightly different. Instead, we give an algorithm which now takes m steps in some sense, but each step is implemented very quickly in m to the epsilon, or m to the little o 1 time, as I've written. So the number of steps is actually much more than previous algorithms, but we can show that each iteration can be implemented very quickly. Okay, what I'm going to tell you about now is just how would you solve such a linear program for the maximum flow problem at a very high level. Let's just think of what a linear program is. We have some polytope in high dimensions where the faces of the polytope are these edge inequality constraints. And since we're studying minimum cost flow, let's say, we have some linear cost, and our goal is to find somewhere close to a vertex of this polytope that's the furthest in this cost direction as possible. A method that was proposed to this is called a potential reduction interior point method, IPM. And the general structure is that you define a potential function on the interior of this polytope, and it has something like the following form. It has two main terms. Here, let's let opt denote the optimal value of this linear program. So it's the minimal cost that we can attain on the interior of this polytope. The first term encourages us, if we want to minimize this potential function, to improve our cost. So as the cost C transpose F goes down, the first term goes down. The goal of the second term is to encourage the algorithm to stay a little bit far away from the boundaries of the polytope. Recall that our inequality constraints were FE at least U and at most UE. So this second term, if we want to keep it small, we want to stay far away from the boundaries. And what you can show is that by minimizing this potential function, that you can actually slowly approach the optimal vertex of the polytope that we're trying to find. How this algorithm looks in the end is that you start at some point on the inside of the polytope, and you take a series of steps, where each step you can show reduces the potential function by about a constant amount. And after taking a sequence of many steps, about m in our case, you get to this optimal vertex, or at least you're very close to it. So that's just a very high level picture of how these algorithms work. Just to tell you a little bit about what these problems that we solve with each step are to take the step. What I mean is here we took a sequence of m steps, and the question is, how do we take each step? It's by solving this problem that I've written right here, which is a min ratio cycle problem. It's a combinatorial graph problem, defined as follows. We have some graph, and on every edge, we have some real number, which is this g vector, and some positive real number, which is this L vector. And our goal is to find a circulation in the graph, or cycle in the graph, that minimizes approximately the ratio between the linear term and the denominator. So for example, in this cycle, the total, just to give an example of how you find the value of a cycle under one of these problems, for this cycle, you can, to evaluate the total length, you can add up all the red numbers, which are the lengths, and get 6. And to evaluate the total gradient, you need to take the directions into account.
Sorry, what is delta?
Delta is the vector which indicates the cycle. It's the indicator vector for the cycle, basically, with directions taken into account. So for the gradient, if we look at this cycle, what you do is for every edge, if the direction agrees with the cycle, you take it with its positive, and otherwise you take it with its negation. So here you can check that the gradient total, the linear term is 1. If I had reversed the direction of the cycle, then the denominator stays the same, and the numerator will negate. All in all, in this problem, what it ends up being is that you have the numerator, which is a linear term, and the denominator, which is some undirected total length term. So what this problem is really asking you to do is to minimize some linear term, like the cost of the cycle divided by its total length. And even if this problem is defined for circulations, which means that just the net demand at every vertex is 0, you can show that the optimal solution is a cycle. Just to recap one more time, that means what the algorithm does in the end is it does a sequence of m steps where during each step you find such a cycle, and then I add it to my flow, and I do this about m times until I'm done. So overall, what the interior point method shows is that we can find a maximum flow with the following sequence of steps. The algorithm takes about m to the 1 plus little o of 1 steps, where each step solves the spin ratio cycle problem. At each step, we don't have to find the cycle exactly. Any crude approximation up to m to the little o of 1 factors of its value suffices. And additionally, over time, the inputs to this cycle problem, this g and l vector, change very few times, about m to the little o of 1 on average. Given this reduction, then we need to show that you can actually solve all of these problems, this sequence of n problems, in total linear time, which is the major part of the paper that I'm not really going to be able to talk much about at all. But given a sequence of problems satisfying the conditions on the previous slide, you can solve all of them in total m to the 1 plus little o of 1 time, and that gives a linear time algorithm for the minimum cost flow problem. Just wanted to say a little bit about directions for the future work. As I said, our algorithm solves max flow, which corresponds to the bipartite matching problem. You can ask about matchings in general graphs, not necessarily bipartite. In this case, it is known that you can use combinatorial approaches to get algorithms running in time m root n. However, the linear programming formulation of the problem actually requires exponential size. So a lot of the things I've discussed today don't work directly. So it would be interesting to understand that case. Also, you can ask about dynamic maximum flow. As the graph changes, can I somehow maintain the value of the flow? Today, I just talked about the static case. And finally, the algorithm ends up being very complicated for a lot of reasons, and it would be nice to have a simpler version of it. So that's all I had. Thanks.
Question to Jan.
In this inner step, why do this combinatorial thing rather than something like a move in the direction of the gradient?
So can you repeat the question?
For this inner step, you do this combinatorial, you solve this. Why not just take a step in the gradient of your objective function?
Good. So the question is, why not just take a step in the gradient? Why do this more combinatorial thing? So I guess there's two parts of that. One is that when you solve this combinatorial thing, this g vector in the numerator actually is the gradient. However, if you want a good convergence, you need to somehow take into account the local geometry of the problem, and not just somehow because you need to take into account the local geometry of the problem, because the polytope, if the polytope ends up being kind of long, then you don't want to just take small gradient steps. You kind of want to take a step in the gradient direction that's as large as possible. And that's kind of captured by the denominator. Now the norm is kind of the more interesting part. Here I use the L1 norm, while previous approaches use the L2 norm. But discussing why that helps is a little more involved. Yeah.
So is this algorithm something that would be practical to implement, or?
This algorithm, as I said, it's very complicated right now, so it's probably not very practical to implement, but yeah. So that's a good thing to think about, maybe.
I'm not understanding. were you able to solve a dynamic version of the mean ratio problem, or you're also only able to solve an approximate dynamic version of the mean ratio?
Good, we're only able to solve an approximate dynamic version. Yeah, yeah. But there's actually even more complications if you need to get it to work for the full algorithm. That we're able to do, basically.
Yeah.
And is there a way to think about it without the IPM framework? I guess the way you phrased it sounded very like.
The question is there a way to think about it without the IPM framework? I guess maybe the way I would say it, where the interior point method is doing a ton of work, is that recall that the original Maxwell problem is a problem on a directed graph, right? Now this min ratio cycle problem, notice that when I'm measuring the length of the cycle, it's actually a very undirected notion, which is that's kind of unintuitive. I start with a problem on a directed graph and I end up wanting to solve some kind of problem where the measurement of like the quality feels much more undirected. So I think that's where the continuous optimization is doing a ton of work.
All right, thanks.